see. Make sure this is all running like it's supposed to. Okay. This information is from Unit 5. It talks about the shape, center, spread. These are 3 things that we had to check condition-wise to kind of go through and make sure that we can use. In Unit 5, we still used a Z distribution only because in those questions, you were given the population mean and the population standard deviation because you were just calculating a probability of a specific sample size. Now that we are kind of going into inference procedures, we are going to have to kind of go back or use the T distribution instead. And it does require still checking conditions, still calculating the interval and the test statistic and the p-value. But again, it's a lot of the same thing. So the 3 things that we check is the normal condition, and that is usually satisfied by central limit theorem if our sample size is bigger than 30. Today, we're going to use some histograms. I went ahead and graphed them for you, but you still have the option of being able to graph in your calculator. If it is an AP question or a test question, I would expect that you would be given the graph. You would have to just comment on you don't see any strong skew and you don't see any outliers. For the most part, everything is going to pass. The other 2 conditions, the center and spread, that is checked by doing randomness and 10%. Now, for the random condition, we have to kind of go in and either see, did they randomly select from the population, or did they randomly assign treatments or the order of treatments or something random in their experiment at all. The only thing that gets kind of wishy-washy in terms of conditions is for the experiments. Oftentimes, we will just come in and say, because we are dealing with volunteers and we are not randomly selecting from the population, we just say that we're going to assume that they are independent, because usually picking a volunteer, you say you want certain criteria, but you cannot guarantee that the volunteer meets the criteria that you need. So usually we just say they're independent in the phrasing, which we'll do today. So these are my like sampling distribution features. The one thing that is going to kind of change, if you notice from our standard deviation formula in the top right to what is down in the standard error, the top right is those special cases where you do know the population standard deviation, that's sigma. In most cases, in all that we do as far as inference tests for means, you don't know the population standard deviation. The only thing you know are the sample standard deviations. So these are sample standard deviations. So only knowing the sample standard deviation calls this measure standard error. It does not mean that it's wrong. It does not mean that it's incorrect. It could be, but it's not saying like, yes, this is wrong and I'm still using it. It's just saying I don't have the population standard deviation, which in most cases you don't, because in order to have the population standard deviation, you have to know the population mean, which at that point, if you know the population mean, why are you doing inference anyway? So it's kind of like a circle of why. So because we rarely know the population standard deviation, we use the sample. This introduces some error, however, it is just referred to as an estimated standard deviation. And a lot of the time, this is going to be given to you in the question because they're going to say, we went out and we collected this sample and this was the mean and this was the standard deviation. So anytime you see S, that is typically given to you in the question itself. Sometimes you do have to find it, which we'll do for our problems today, but I'll kind of run you through that in the calculator when we get there. So center, spread, and we have shape. Then we go into degree of freedom. So when it comes to degree of freedom for to sample, the formula is very complicated. It is a very big formula. And one thing that we will say, you are never, ever, ever expected, if you are doing this by hand, to have to calculate the exact degree of freedom. That is only there just to show you why when you go to the calculator and you use stat tests and you go to the interval or you go to the test for to sample, they're going to report a degree of freedom to you that looks different than what we're going to write when we do it by hand. The reason being is the calculator is going to go in and it's going to calculate the exact one using this formula. Now, what I kind of said as a disclaimer in first period was, even though these numbers are different, even though they can be sometimes really different, you are not ever going to encounter a question where it is so different that you would come to a different conclusion. So a lot of the time they trial run those AP FRQs many, many times, and they see, okay, how is someone answering this? How would they answer that? What kind of answers are they getting here and in the calculator and by hand? And they are going to pick questions where you would come to the same conclusion no matter what method you choose. So even though, and we'll see in our example, it's going to be a very different degree of freedom, our numbers still end up being fairly close. So when you are selecting degree of freedom for 2 samples, you're always going to pick the smaller of the 2 sample sizes, and you're going to either decide to use the first sample or the second. So you're going to look at both of the sample sizes, pick which one is smaller, subtract 1 from that. And then this is considered the conservative degree of freedom. It is what you will use by hand, and confidence intervals will have a margin of error as large as or larger than is needed when you're doing the conservative. And the significance test gives a p-value equal to or greater than the true p-value. Again, if you are worried that this is going to be so far off, don't worry. They, in their grading, will always have something that is calculated by hand, and they will have something that is calculated using the TI, and they will have both available for your grader to see, do they have one of these? Because there are people who choose either way. So we will try both today. We'll do one by hand, check it in the calculator, one by hand, check it in the calculator, and we'll see how they compare. So the first one we're going to do, we're just going to jump right into it. We're going to do a confidence interval. So for a confidence interval, we have a formula, and it should look fairly familiar because we have done something very similar when it came to 2 sample proportions. We are going to take x1 bar minus x2 bar. Those are your 2 sample means. And then we are going to add and subtract. Remember, this entire second half, this whole t star, square root, and the standard error formula, this is all that makes up the margin of error. So it's still a point estimate plus minus a margin of error. Now, in this case, we go in, we add the margin of error, we subtract the margin of error. That is what creates our lower and our upper bounds for the interval. Remember, a confidence interval is a range, an interval, of plausible values for whatever you are looking at. For us, in these questions, we're looking at the true mean difference between 2 different populations. So, example 1 says, observational studies suggest that drinking at least 4 cups of coffee a day reduces strokes. This is believed to be because coffee contains a range of plant-based compounds called polyphenols, thought to promote healthy blood vessels and dampen inflammation. In an experiment, 20 healthy women were assigned at random to drink 3 cups of regular coffee a day or drink no coffee for 2 weeks. If I drank 3 cups of coffee a day, I would be buzzing. That's a lot of caffeine. Here are the percent changes, and I think I wrote this incorrectly. This should be after minus before. Let's change that. Huh? I know. I only caught that it was wrong because first period told me that didn't make sense, and I was like, ooh, you're right. After minus before of the polyphenol levels for the subjects in both groups. So the goal of this whole thing is we're trying to see if the people who drink the 3 cups of coffee a day, are they going to have increased levels? Is the percent change going to be higher? So when I do after minus before, I do want to see positive outcomes because the after, I want that number to be bigger than the before, the smaller. One of the hardest things I think people have when it comes to the matched pairs and the 2 sample anything, proportions or means, is kind of realizing, do I want a positive difference or do I want a negative difference? And it really just relates to, what is your end goal? Our end goal is that these polyphenol levels increase, because that should hopefully help prevent strokes. Now, we're not testing, does it actually prevent the strokes? We're just trying to see, does it increase the level of this thing that could potentially help? So it goes on to say, construct and interpret a 90% confidence interval. So that's going to be important when I'm doing this by hand in determining what my T-star level or T-star number is, for the difference in mean percent changes in polyphenol levels for the coffee and no coffee treatments. Here is where I'm going to kind of do my matched pairs disclaimer. Something is only matched pairs if they are saying within the question that they are going to specifically tie one person to another, or they are going to specifically have one person do two things. If you do not see that, if you do not see anything in the question noting that we are going to find two people who are very similar and one person is going to get coffee and one person is not going to get coffee, that is not matched pairs. They are taking two separate groups, two completely separate groups of people randomly assigned to these treatments, and they are only getting one treatment. So usually, if you can kind of narrow down how the experiment is given, which it should tell you in the question, that is going to help you decide between, is it matched pairs or is it two sample? I know it looks a lot like, if I see this table of data, I should be subtracting them. I should be looking at one sample, making it a matched pairs. But the values that I have don't necessarily reflect one person doing both the coffee and the no coffee, or us saying that we found two people who were very, very alike or who had a natural pairing. We do not have that. So because of it, that's what makes it two sample. Now, in order to do this by hand, I do have to get some sample statistics. So I went ahead, I put my data into L1, I put my data into L2, and I ran one var stats for each. So this is not something that I normally recommend, simply because it does require a little bit of extra work on your end, but I'm going to kind of walk you through it. You don't have to, I would put the data in your calculator because we are going to run the test, but you don't have to follow through these steps. You can kind of just listen along. I am going to go to, I have my data in stat edit, L1, L2. I'm going to go to stat calc, and then I'm going to go to one var stats. I'm going to run them for L1, and I got my X bar, my S, and my N. So I did that for both sets of data, which is where those summary statistics are coming from. This is one of the reasons why I don't recommend, if you have data, doing it by hand, because I had to already go through the effort of putting the data in my calculator anyway and running to get these summary statistics. So at this point, I've probably done enough work where I could have already ran the test in my calculator. So this is just an added step for us because we are going to do it by hand. Now, I have all my data in my calculator. I'm not going to make you go through the process of finding the histogram because I did provide them for you, but just to kind of talk about what needs to be written in that place. So we have random, we have independent. This is an experiment. They did not say, if I'm remembering correctly, that they went out into the population and they randomly selected these women. They have these 20 women who volunteered or were signed up for this experiment. And usually if you are doing something where you're making them do something, intake something into their body, even if it's coffee and people like coffee, it's usually not ethical to randomly select from your population. And a lot of the time, even if you're like, well, I'm still gonna try, I'm gonna randomly select and see if they want to participate, that still introduces bad experimental design because people cannot elect to participate or not in a truly randomized selection. So subjects were randomly assigned treatments. Subjects are assumed to be independent. This is only because I don't necessarily know what population these 20 women are representing. Yes, they're representing women. However, I cannot say that I sampled from all women, so I can't generalize it to the population. So we're just going to assume they're independent. Now here is where we kind of look at the graphs and we decide, is it normal? Is there skew? Are there outliers? And I will say, we take this kind of with a grain of salt. If it looks to be normal and it looks okay, we say, you know what, it's fine. So I usually, and this is going to be important when you are doing conditions for a graph that is provided to you. You cannot just lead to the conclusion that there is a sampling distribution that is approximately normal. You have to go in, and especially when there's two of them, and you have to say that both histograms show no strong skew or outliers. That is kind of like us saying, my sample size is bigger than 30 and CLT tells me this. So they will be looking for something indicating, why did you determine that it's going to be normal? You can't just look at the graphs and be like, yeah, it's normal. They want reasoning, especially because it's kind of like an exchange of, we're going to do this, so you have to do this. Especially in cases where they provide you with the graph. You just got to write the sentence saying, yep, the graph looks no strong skew, no outliers, great, move on. And I will say, if you are sitting on the FRQ, they are not going to try to trick you. There's not going to be a point where you get here and there is skewedness, because in our next one there is some slight skew in the graph for the next example. There's not going to be a point where they're like, yes, they should be stopping, and they didn't stop, so we're going to fail them. Most likely, they want you to still go on with the test. I will recommend, even if you think all three conditions fail for some reason, do the test still. Just because I don't think that will happen on the AP exam. I don't think that they're going to give you something where the conditions are going to fail and they're going to expect you to stop. They will not expect you to stop. They'll want you to keep going. And in the conclusion, you're going to write something that says, but all of the conditions failed, so maybe this is wrong. Something along those lines. So this is a 2-sample T interval for mu1 minus mu2. I'm going to go ahead and take all of those summary statistics that I just found, and I'm going to plug them into the formula at the very top of the page. Now, the only thing that I don't have written here, which I will write to kind of explain in just a second, is how I exactly calculated T star. The only reason I didn't want to write it here is because I don't want you to think that you have to show this work. Is it helpful? Yes. Is it probably going to be beneficial? Yes. But it's not something that they require as a necessary part of their grading. So what I did in order to get this 1.8331, I went to inverse T. Now, the one thing that you have to remember is when I have a confidence interval, it is always centered in the middle. So if I am trying to find a T interval that's 90%, that means that there's an area of 0.90 in the middle of my distribution. And this area, it has bounds. The lower bound is going to be the negative T star. The upper bound is going to be the positive T star. Now, they do not care which one you find. It is going to be the same number. It's just the lower one will be negative, the upper one will be positive, and you can technically find either one. If there is 90 in the middle, that means there's 0.05 in the left tail and 0.05 in the right tail. So you can go in and you can enter in an area of 0.05 and the degree of freedom, and you're going to get this value. I always go for the positive one, and I've mentioned it before. The reason why I do this is even I struggle with decimals and percents sometimes, and when I have something like I need 0.5%, and that is the decimal 0.005, like my brain and the numbers, they get weird. So I can easily know like 90% and 5% is 0.95. And I can know 95 and 2.5 is 975. And that makes it a little bit easier to enter in the area. But the other one would also give you what you need. The reason why we have to do this, if I wanted to get all the way to the positive T star, because our calculator is reading from the left-hand side to when you tell it to stop, we have to include that entire area. So that's why I'm doing 0.95. Degree of freedom, we pick the smaller sample size, we subtract 1. In our case, they are the same sample size, so this 9 is just going to come from 10 minus 1. Plug all this into the calculator, do a minus, do a plus, you get your lower interval, you get your lower bound, your upper bound. Now, just to kind of relate this to the calculator, because again, if you have data, my recommendation is just use the calculator. Because I had to already, before I even got to plugging this in, I had to find those statistics individually. Now, I'm going to, if you have your data in your calculator, you're going to want to go to stat tests. And for the t interval, we're going to go all the way down to option 0. That is the 2-samp t int. And then you have the options we did for the 1 samples. You either have data or you have stats. Stats would be the question gives you summary statistics. And then I'm going to change mine back to L1 and L2. Oops, not L5. L2. And then you should leave your frequencies at 1. We're going to keep our confidence level. If yours says 0.95, change it to 0.9. And then you want to say no to pooled. We will say no to pooled for everything related to confidence intervals for these. And then we hit calculate. And what you should notice is we are going to get an interval that is kind of close to what we have, but it's not going to be drastically different. The only reason it's different at all is because they have an exact degree of freedom, which they calculated to be 17.9, and we have a conservative degree of freedom. But again, notice the numbers that we have are not completely different than what they have. And that should always happen even when you use the conservative method. If you are doing the calculator, write down the degree of freedom that they have on the screen. Don't just be like, okay, I have the interval, I'm going to go back and now I'm going to write the degree of freedom as 9. Stay true to your method. If you are doing calculator, everything's going to come from the calculator. If you're doing it by hand, use it by hand. Don't just go in and jump in and use the degree of freedom that's exact and conservative, switching them out. Calculator all the way or by hand all the way. So, and don't worry about having to write down the steps. I have a whole table at the very end that you're going to have that summarizes all of the calculator stuff. Same sentence. We are 90% confident the interval from 2.5865 to 6.8935. I try to include a unit when I can. These are percent changes. Captures the true difference in polyphenol levels for coffee minus no coffee treatments. And I'm going to add in my 4 subjects like these. I think I left it off on this one. It is important that when you are doing either the matched pairs or the 2 sample, that you do include the word difference because they are calculated differences. We are getting the difference between the coffee group and the no coffee group, and we are seeing those calculated values. Now, the reason why that is important, when I am looking at coffee minus no coffee, the last question says, does this interval suggest that coffee is more effective at producing polyphenols? Well, if I want coffee to be more effective, then I want the coffee numbers to be higher than the no coffee numbers. So remember, again, we are doing coffee minus no coffee. And if I want the coffee to be higher, I am interested in having positive values. I want a positive difference between those 2 things. And so a lot of the time you can kind of get away with being like, well, 0 isn't in the interval, so we can't conclude that they are the same for the most part. This is not that question. This question is asking, is coffee more effective? Meaning, is coffee higher than no coffee? And if you look at our interval is entirely positive. And so because the interval is entirely positive, it does suggest that coffee is more effective at producing polyphenols. If I even had one negative number, if I had one difference where it was just like negative 0.00001, one time, it would say, because the interval is, this is all of the possible values, it is possible that it's not better. So that would be something where I would say there is not evidence. But because the interval is entirely above 0, meaning it does not contain 0, it suggests coffee is more effective. And this kind of goes into, you could technically, if you wanted to, write hypotheses for this. You could say mu of 1 is equal to mu of 2, and then you could say mu of 1 is greater than mu 2. And then you would see, if I moved everything to one side, I want all of the numbers bigger than 0, which is another way to kind of approach this, but you can just kind of think of it as, do I want a positive difference or a negative difference? And that also helps. I will say this, even though you can technically write hypotheses for this, if you get a question like this, they are not going to want you to answer it with a significance test. Even though you do have enough data, you do have the possibility of going into your significance test and getting a p-value and the t and actually coming to a conclusion. If they say, based on this interval, they are going to want you to relate your answer to the interval. And usually, if I'm remembering correctly in the grading, they do not give you any credit for that. If you just go in and did the significance test and said, we reject the null, there is convincing evidence that coffee does increase polyphenol levels, you still get no credit for that because you did not relate it to the interval. Now, second thing, we have the significance test. So this one is going to, again, feel pretty similar. The only thing that might seem a little bit off is the x1 minus x2 being the only thing in the numerator. Remember when I have my null is mu1 equals mu2, another way of writing that is mu1 minus mu2 is equal to 0. So that means the null proportion, the mu naught, is 0. So technically, if you wanted to, you could even go as far as to say we are subtracting 0 from that difference. But it's not required, it's not necessary, it does not have to be there. So that's why we usually don't have it. These are going to be my null hypothesis and my alternatives possibilities, just to kind of go in and give you some examples. I can have HA mu something to 0, or let's do mu1, mu2. We'll use that. And this could either be less than, it can be greater than, or it can be different, not equal to. Is there a change? Any of those phrasings can kind of fill in that blank. So it will come from the question. You should never get a significance test question where you don't know what the alternative is supposed to be. They will give you direction on what they want you to do. Okay, so I am going to do this one by hand, and then I'm going to run through and I'm going to do it with the calculator. Again, if you have tables of data, my recommendation is always going to be to just run it in the calculator, because either way you're going to have to get summary statistics. I did go in and get summary statistics in the same way that I did for the last example, just to kind of show you that it is possible, because I do have some people who favor the formulas. You can still do it. This particular problem is asking, does increasing the amount of calcium in our diet reduce blood pressure? Examination of a large sample of people revealed a relationship between calcium intake and blood pressure, and the relationship was strongest for Black men. Because observational studies do not allow cause and effect, a randomized experiment was designed. So we are going to go in, and they have 21 healthy Black men who volunteered. So as soon as you see that they volunteered, immediately you cannot generalize to the population because you did not sample from the population. To take part in the double-blind experiment, we can establish cause and effect. Because it is an experiment, we just cannot generalize it. They were randomly assigned to 2 groups. 10 received calcium and the other 11 received a placebo. The response variable is the decrease in systolic blood pressure for a subject after 12 weeks in millimeters. And here's where it got confusing. And if I was truly like, I don't want to say that, I would have just changed it. But an increase appears as a negative number. So I know that's going to seem kind of wonky for some of us. So any negative number that I have is actually increasing. So truthfully, they probably did what I had in the other question, a before minus after, meaning they should be getting a negative number. But we're just going to keep that in mind because that's going to come into play with how we write our hypotheses. Any negative number is actually they are increasing their systolic blood pressure. So we don't want them to be negative numbers. We want them to be positive numbers because that would be a decrease. So does the data provide convincing evidence that a calcium supplement reduces blood pressure more than a placebo? So I went ahead, and you don't have to always use mu1 and mu2. You can relate it to what you are doing in the groups. I did mu C for the calcium group. I did mu P for the placebo group. The null is going to always be that they are equal to each other every single time, no matter what. In any case of any hypothesis you ever write, the null is they are equal. It is equal to the claim. It is equal to the number. Whatever is going on, they are equal. And it says we want the calcium supplement to reduce blood pressure more than a placebo. Now, here's where the backwards thinking happens. I want the calcium to reduce, but a reduction is actually shown as a positive number. And so if that is the case, when I write my alternative, I need it to be that mu of C is greater than mu of P. And it's only because within the phrasing of the question, they said an increase is represented by a negative number. Most likely they subtracted their ending value or their starting value minus their ending value, probably. That's my best guess. Now, here's where my that kind of does look a little skewed, but we're going to say it's fine. I literally copy pasted what was on the other one because all of those same conditions are met here. Subjects were randomly assigned treatments. Subjects are assumed to be independent. They had volunteers. They were randomly assigned to either get the calcium or the placebo. And because I don't necessarily know that they're representative of the population, yes, they are Black men that volunteered, but are they representative of all Black men? I don't know that. So we are just going to say we are going to assume that they are independent. Then, because that's what 10% is checking. The last condition is a little wishy-washy. It's a little sure, we're going to believe that. The one on the right, the one for the placebo group, for the most part, seems pretty normal. No strong skew, no outliers. And here's why we use the phrasing strong skew. Because we can kind of look at the left group and be like, that looks somewhat skewed, but does it look strongly skewed? We're going to say no. So no strong skew or outliers. The sampling distribution is approximately normal. The one thing I did change between the two things, in the confidence interval one, we should be using the X bar, and in the hypothesis test, we always talk about the population, which is why I have mu1 minus mu2. But this is exactly the same thing I wrote for the other question. And truthfully, if you are doing an experiment where you did not sample from the population, those first two statements can be reused and recycled again and again, as long as they randomly assign the treatments. Then we go on and we actually calculate. So we are going to perform a 2-sample t-test for mu1 minus mu2. This is going to be where I'm going to take those summary statistics. Now, no, I did write them separately, whether you copied them down or not. It's not a huge difference. It's a huge deal. It is not something that you have to write separately on the AP exam. Say, for instance, you're like, I completely forgot what calculator function it is, but I did enough with the formula chart where I put together how to get T. I got all my data from my calculator. Great. All you have to do as a part of your work is take those values that you have and plug them into the formula. You don't necessarily have to come out and say, X1 is this, X1 bar is this, X2 bar is this, S is this, S1, S2, N1, N2, whatever. They know, your graders know what the formula is for a 2-sample t-test. So they know when they see 8.7433 squared, that is the standard deviation squared. They know those values. So going in and just plugging them in is enough. That is enough for you to have. And so the only reason that I have 5 plus 0.2727 is because that second mean was negative. And so because the second mean was negative, it actually 2 negatives made the positive. That's why it's plus. It is minus normally, but that is where it's coming from. So I got my t value. Again, reminder, this is your test statistic. And I always think that knowing how to do the significance test by hand is important over the interval, because they ask a lot of questions of, if we give you this t value, what is the p value? And you have to know, once I know my test statistic, I have to go to TCDF in order to calculate the p value. So I am going to actually do that. I'm going to go to TCDF. So in this case, whenever we are doing a greater than, because my alternative was mu of c is greater than mu of p. Actually, that means, truthfully, I should change these. I'm going to change it to c and p because I want them to match. Mu of c, mu of p. If it's positive, we are going in the more extreme direction, so we're shading to positive infinity. The reason why I picked 10 or 9 is my smaller sample size was 10, and I subtracted 1, and I got 9. The other sample size was 11, so 10 is smaller than 11. Plug this into my calculator. This is in the second VARS menu. There's really only 2 places you should be when you're in AP Stats, second VARS or in the stat menu. Somewhere in between those 2 places, you're gonna find everything that you need. And then we get our p-value of 0.0716. Now, just to kind of show you how this works in your calculator, you don't have to type all the data in if you don't want to, but I went ahead and I put my data into my lists. They are actually in my L3 and L4. And then to run the test, we are going to go back. There's 2 places you should be, stat test or second VARS. We're going to stat test. This one is going to be option number 4, the 2-samp t-test. And then you tell it what lists you have. We have mine will be L3. L3 and L4. Oops. And then you say frequency 1, you pick your alternative. I want mu1 to be bigger than mu2. Always say no to pooled for these and hit calculate. And you should get a T and a P that is fairly close even when you are doing the conservative degree of freedom. This has a degree of freedom of about 16, and we still got a very similar T and P value. Now, here again is my disclaimer. Even if they go out and they pick something and it is different, it should never be different enough that it is going to cause you to come to a different conclusion. And if it is the case, if it is something where if you did it by hand, you got 0.04, and if you do it in the calculator, you get 0.05, and then you would have failed to reject versus reject, they are going to give you credit. It's not going to be well, yours doesn't exactly match what I have, it is wrong. They're going to give you credit when they can. They're going to follow your work. Even if you have the wrong T and the wrong P, they're going to look at, did you interpret it correctly? And you still will get credit for that correct interpretation. So since the p-value of 0.0716 is greater than alpha equals 0.05, we fail to reject. There is not convincing evidence that, and here is where I go in and plug in my context. A calcium supplement reduces blood pressure more than a placebo for subjects like these. Because because there is a 7% chance of us getting this particular sample, which then would lead us to saying that it's pretty likely to happen just from random chance alone. Oops.